Hello grade 11s and welcome to question number 4 in this series of videos on the paper 1 exam. So this question involves electromagnetism. We're going to be looking at those magnetic fields around current carrying conductors, and we're also going to look at how a changing magnetic flux can induce current in a conductor, and that is Faraday's law. So if you take a look at your formula sheet, you're going to see this formula that you need to be familiar with, even though you will not be performing calculations with it this year as a result of the pandemic. So this formula is based on Faraday's law, which says that a changing magnetic field induces an EMF in a conductor. The symbol on the left-hand side stands for EMF. We say that this magnitude of the induced EMF is directly proportional to the rate of change in magnetic flux. Now, this is not the way in which you need to define Faraday's law, but it is a good or worthy way of stating Faraday's law. In this case, we know at the top we have the changing magnetic flux, at the bottom we have change in time, and this N over here on the side, that is the number of turns in the coil. So we're going to be looking at solenoids, for example, in this section, and the N is for the number of turns in the solenoid. So let's now look at the questions. Question number 4.1 says, a current passes through a straight conductor called Lm as shown in the diagram below. Draw a diagram of the magnetic field that forms around the wire Lm. So as a starting point, we of course are going to draw a wire. So here is the wire. I'm actually going to change the color of this wire. Let's instead use a black pen. So there is the wire. Now, in order to determine the direction of the magnetic field, we first need to determine the direction of the current that is inducing this magnetic field. Please remember that when we use the term current, we are referring to conventional current. That is the flow of positive charges from the positive terminal of a battery to the negative terminal of the battery. Truly speaking, we have electrons flowing through the circuit, but we don't refer to electron flow as current. Electron flow is called electron flow. Current is the flow of positive charges from the positive terminal to the negative terminal of the battery. So which terminal over here is the positive terminal? Well, if you're looking at the positive sign, can you see it's made up of two lines? We can take the one at the top, erase it, and add it on to the first one. And now we have a long line. If we look at a negative sign, it's just one line, right? So this is a way of remembering that the longer side is positive and the shorter end is the negative terminal. That means that in this circuit, positive charges are going to flow in this direction. And we therefore now know that charge is going to flow from L towards M, and we're going to indicate this on the sketch. We see that it's out of 3 marks, so we're going to assume that one of those marks is for indicating the direction of the current. Now that we know the direction of the current, we're going to have to make use of the right-hand rule. Now here's a picture of the right-hand rule. We know that the thumb points in the direction of current, and our fingers, the 4 fingers, are going to turn or curl in the direction of the magnetic field. Now in this case, our current is downwards. So what we're going to do is we're going to take this diagram and we're going to rotate it. Of course, you're going to just take your hands and you're going to turn your hand around. So let's just quickly move this to the front. And if we now compare this diagram with the one on the left, we can clearly see that on the right hand side, and we're going to do or show the magnetic field by making use of circles. We don't need to include many of them. On the right hand side, using this right hand rule, we see current is going to come out of the page. So we put dots at the center of the circles. On the left hand side, the magnetic field lines, magnetic field lines. On the left hand side, it's going to go into the page. So here we're going to draw crosses. Okay, and we have now used the right-hand rule in order to determine the answer to question 4.1.1. I'm going to award 1 mark for the direction of the current, 1 mark for showing the correct symbol for out on the right hand side, and 1 mark for the correct symbols for in on the left hand side. And that is your answer to question 4.1.3 for 3 marks. Question 4.1.2 now says, write down the rule which is used to identify the direction of the magnetic field. Now, I unfortunately do not have the memo to this problem from this paper. It's not available yet, but I'm going to assume that they mean the name of the rule. If they mean the name of the rule, we're going to call it the right-hand rule. And that is going to get us 1 mark. I'm assuming that it's the name of the rule, because if we're going to be stating the whole rule, I would personally award 2 marks. But if you would like to write down the whole rule, you would state something as follows. Hold the straight conductor in your right hand so that your outstretched thumb points in the direction of conventional current. Your curved or curled fingers around the wire indicate the direction of the magnetic field. So either or, and you're going to get your marks. Question 4.2 says the setup of apparatus below was used to demonstrate Faraday's law of electromagnetic induction. And we see here a magnet that is entering a solenoid that is connected to a galvanometer or galvanometer. Question 4.2.1 says, state Faraday's law of electromagnetic induction in words. For 2 marks, you're going to say, the magnitude of the induced EMF across the ends of the conductor is directly proportional to the rate of change in magnetic flux linkage with the conductor. And that is going to get you 2 marks, in this case, all or nothing. Question 4.2.2 says, write down the polarity, north pole or south pole, of the end of the solenoid at point T as the bar magnet approaches the solenoid. Now, to answer this question, you actually need to be familiar with Lenz's law. And Lenz's law basically says the following. It says the direction of the induced current is such that its magnetic field opposes the change that initially produces it. So what that means is if we are bringing a north pole into the solenoid will want to produce a north pole on the left-hand side of it so as to oppose or repel this north pole, because north repels north. So based on that, we can come to the conclusion that the correct answer is north pole. And for writing down the answer north pole, you're going to obtain 1 mark. Question 4.2.3 says, why does the galvanometer needle deflect as the magnet is brought closer to the solenoid? To answer this question, we're going to simply state the following. We say that a changing magnetic field around a conductor induces an EMF as well as an electric current in the conductor. And for writing this down, for stating that a changing magnetic field is going to lead to the current being induced in the conductor, we're going to obtain 2 marks. We have basically stated what electric or rather electromagnetic induction is. So now we can go on to 4.2.4. It says the bar magnet is then held stationary inside the solenoid. Write down what will be observed on the galvanometer. Give a reason for the answer. We know that if it is held stationary, if the magnet is held stationary, then we do not have a changing magnetic field. We can therefore say that the galvanometer needle will not deflect. For this, you're going to obtain 1 mark. Then your reason will be the magnetic field is no longer changing and therefore no current is induced. Remember, a changing magnetic field is needed to induce a current. So that gives you your 2 marks to question 4.2.4. 4.2.5 says, in which direction will the induced current flow? Write only from x to y or from y to x. We're going to be making use of a right-hand rule here as well. In this case, however, we know that the thumb is going to point in the direction of the field, which exits at north. So inside of the solenoid, we point from south to north. Our thumb points in the direction in which the field is going to exit. Okay, so field lines, magnetic field lines, are actually continuous lines. Therefore, our thumb points towards the left, and we see that the fingers, which show the direction of the induced current, curl around the solenoid, as you can see in this image. Therefore, if we are looking at this diagram, we can clearly see that the current is going to flow up like this. It's going to flow down past x towards the right and up at y. The correct answer to 4.2.5 is therefore from y to x. Nope, sorry, that is incorrect. It is from x to y, and we simply write down from x to y because that is what we've been instructed to do. Don't elaborate, don't change the statement, write down exactly what they say, because for this you're going to obtain 1 mark. Now question 4.2.6 says, state 2 ways in which the magnetic field of the induced current can be increased. To find this answer, we can simply go to this formula, and we can therefore say we can move the magnet into or out of the solenoid faster, so we can reduce the change in time, so that's a smaller number, or we can increase the strength of the bar magnet. We can make the magnetic field stronger. We can use stronger bar magnets because that is going to lead to a larger change in magnetic flux. Or we can increase the number of coils in the solenoid or number of turns in the solenoid. For writing down any one of these 2 changes, you're going to obtain 2 marks, 1 for each change mentioned. And that brings us to the end of question number 4. In the next video, we're going to take a look at question number 5, which is a question on electric circuits. I hope that you'll join me there.